So as I was saying yesterday, as I was saying previously, I conducted an experiment on these same values, and this was the graph I had. But for the sake of the current experiment, I am going to clean this graph and plot a graph with the values we have gotten today, so that you understand how this graph is plotted. Thank you. So we were generating our table of values. So from the experiments, these are the values we have. We have 28.00, 28.00, 28.00, 28.00, 28.00. So our theta 1 was 40.00. We have 32.00. These are the fresh value we got in today's experiment. And then we have 35.00, 35.00. We have 34.00. We have 33.00. We have 33.00. So here we have 12.00. We have 4.00. We have 7.00. We have 6.00. We have 5.00. So these are the values we got. So we are plotting a graph of this, a graph of mass, of this mass on the vertical axis, and theta on what? This is theta. Sorry, this is theta. Theta on the x-axis. So we are going to quickly choose the scale for this experiment right now. Please take note. This is what we just did. You can screenshot it quickly. So we're going to use this line as our vertical axis. You draw a straight line here. You draw a straight line here with an arrow up. Let me confirm the graph quickly. Yeah. Plot a graph of M. Yes, the graph of M on the vertical axis. So this is M in grams. You must label your axis correctly. So M in grams. And then we're also using this as our horizontal axis. So for the horizontal axis, we will draw this line. This line is not too visible. Let me use the other marker. So we have a line here. So you put your arrow this way. So this is a theta degrees. The next thing we are going to do is to choose a suitable scale for this graph. For the masses, the highest value here is 250 grams and the lowest value is 150 grams. So we are going to choose a scale in such a way that it will accommodate the highest value here. So let's try to see. So this is very close to YX standard graphs. If you can count very well from, let's count. This is 1, 2, 3, 4, 5. That is 1 unit. And then 1, 2, 3, 4, 5. So from here to here is 10, that is 2 cm. So from this point to this point is 2 cm. So let's try 4 cm to 100 units. Let's see. So this is from here to here is 4 cm. So this is 100, this is 200, this is 300, this is 400. So on the vertical axis, we are saying the scale for this graph is 4 cm is to 100 units on n axis. That is the y axis. And then the highest value, so let's plot it quickly. This is 4. So write 100. This is another 4. We write 200. It's another 4. We write 300. It's another 4. We write 400. So all physics graph, a good number of them will start from the origin. So this is 0, 0. And then the highest value for theta is 12. And the lowest value is 4. So we are going to say, let 2 cm, let's check and see. This is 2, 4, 6, 8. It will go. So let's say 2 cm to represent 2 units. So we say 2 cm to what? 2 units on theta axis. That is x axis. So each 2 cm we add 2. So this is 1, this is 2, this is 4, this is 6, this is 6, this is 8, this is 10, and this is 12. Now, the next thing I would love us to look at before we proceed is the value for each of these small box. Very, very important. We choose 4 cm here, meaning 4 cm here will give us 20 small boxes. So 1. So we say that 100 divided by 20 will give us 5. So the value, so we say 100 by 20 will give us what? 5. So the value for each small box here is 5. Here we have it as 2 divided by 10. So 2 divided by 10, so we'll say 2 by 10. The value for each small box here is 0.2. That's the value for each small box here, 0.2. So we are going to plot the graph proper right now. So from the data we collected here, let's start. So if this is 100, here is 150. So this is 150. If this is 200, here is 250. This is 250. If it's 200, this is 350. So this is where our graph will stop. So when the volume of water was 150, theta was what? 12. This is 12. So you trace this line straight up where 150, where the line where 150 and this 12 intersects. That is the point we plot. So this is This is 150. What? This is 150. 150 and 12 intersect here. This is where they intersect. So this is 1 point on the graph. So when the mass of water was 200, theta was 4. This is 4. Where is 200? Up here. When the mass of water was 250, theta was 7. If this is 6, 7 is somewhere here. This is where 7 is. So 7, we meet with 250. Where is 250? You trace it up here. This is 250. So this is where 7 is. So you put a dot here and a circle. So when the mass of water was 300, theta was 6. Where is 6? This is 6. Where is 300? 300. This is 6. This is 300. So we'll put 300 at the point here. So when the mass was 350, theta was 5. Where is 5? 5 is somewhere here. This is 5. So you trace this point up here. This is 350. So you put the dot here. So this is the graph we have. Sorry, there was a mistake here. 250 is on 7. So we clean this. 250 is on 7. So this is 250. This is 7. So this is where the point. Yeah, this is it. So 250 is on 7. So everything is correct right now. So 350 is on 5. 300 is on 6, correct. And 250 is on 7, correct. And then 150 is on 12. So the points are correctly plotted right now. Now the next line of action is to draw what we call in physics the line of best fits. So obviously these 3 points will give us a line of best fits. This point falling this way and this point falling the other way. In every experiment is what I call the black sheep value. There are values that always say I must not go in line with the other values. So this is our graph. So we draw this straight line. This line is not visible enough. I will draw it again. So, follow me. This is a graph. So we have a point here. We have a point here. So there's this point is this way and this point is, so if you measure very well, the distance from this point to here may be the same as the distance from this point to this point. So this graph is a very good graph. The next thing is to draw our large triangle. For our large triangle, we pick this point. We pick this point as our large triangle, and we also pick a point here. So we draw a line here straight. We draw a straight line here. And then another straight line here. You have to draw this triangle as big as it must be. If you draw a very short, if you draw a small triangle, you will lose a mark. So you put a dot there, and then dot. So also dot, and then dot. So this point is called, this is your M2, and this point is your what? M1. Likewise, this point is your theta 1, and this point here is your theta 2. So what is the slope of your graph? Let's write. The slope of your graph is given as change. So this way we call it change. This is change in n. And here we call it change in theta. Replicate what I am doing on the board exactly in your notebook. This is a standard for all straight line graphs in physics. I give you time to look at it very well so that you will take notes. So this is changing, this is changing this. So our slope now is what? Change in n divided by change in theta, which simply means m2 minus m1 divided by theta 2 minus theta 1 on the graph. If you do that, your m2 here is 400. So this is 400. 400 minus m1. Your m1 is 100. You have 100. Divide by theta 2. Theta 2 here is what? To get the exact point, we said the value for each small box here is 0.2. So it says 0.2 times. This is 10, 20, 30, 40, 50 times 51 times 51 to give you 10.2. So 10.2 minus 4. What do you have? So you have 300 divided by 6.2. 10.2 minus 4 gives 6.2. So you have 6.2. If you do that, so we have 300 divided by 6.2. What do you have? You have 300 divided by 6.2. What do you have? You have 48.387. Exactly the figure I got yesterday. I got 48.39. So approximately your slope S is equal to what? Approximately 48.39. What is the units? This is grams. Grams per degree Celsius. This is your slope for this experiment. That is the slope for this experiment. So the next thing we are going to look at right now is to answer the remaining questions in the experiment, and then we'll be done. So this is our slope. We are done with it. This is the value of the slope. So we'll quickly copy this value somewhere. So that we need our slope S. Our slope S is given as, let me record it down, as 48.39 gram per degree this. So that's the value of the slope. So we are done with this stage. We are done with this stage. We are done with this. 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 And then we are here right now. They ask us to evaluate K is equals to 50 all over S. K is 50 all over S. So what do we do? Quickly, I am going to clean this so that we will have time to solve the other questions. Yes. So evaluate, that is B. That is question number XIII. So yeah, XIII. So they say evaluate K is equals to 50 all over S. But slope S is equals to what? It's equals to 48.39 gram per degree Celsius. That is it. So we're saying this implies that K is 50 divided by 48.39 grams gram all over what? Degree Celsius. So what do you have? You have 50 divided by 48.39. If you do that, you have 1.033. What is the unit? What you have here is like this. You have 1 all over G over degree Celsius. So if you evaluate this, you're going to have 1 all over G times degree Celsius all over 1. So our unit here is degree Celsius, degree what? The unit for K is degree Celsius per gram. This is the value for what? K. Degree Celsius per gram is the value for K. So we say therefore our K is equal to 1.033 degrees Celsius per gram. This is the value for K. The next thing we are going to look at is the answer to state 2 precautions we took to get accurate result for this experiment. In the experiment, you made use of the thermometer and the measuring cylinder. So one of the precautions here is that I avoided error due to parallax when measuring water in the measuring cylinder, or you can say I avoided error due to parallax when taking reading on the thermometer. That is one precaution. Choose any of that and say as one. Number 2, I close all the air source to avoid air interference in the experiments. So I believe we are done with that. The next line of action is they ask us to define specific heat capacity. That is BI said define specific heat capacity. The specific heat capacity of a substance is defined as the quantity of heat energy that is required to raise the temperature of the entire body by 1 Kelvin or 1 degree Celsius. The next line of action is they ask us to calculate, to solve for the time taken for heat energy to be transferred to a system in question BII. So let's look at the question together so that we will solve and get out of this place. So if you can look at the board, I read an electric heater an electric kettle rated 1.2 kilowatts is used to heat 80 grams of water initially at the temperature of 20 degrees Celsius. Neglecting heat losses, calculate the time taken for the kettle to heat the water to its boiling point. Take the boiling point of water to be 101 degrees Celsius and the specific heat capacity of water to be C equals to 4,200 joule per kilogram per Kelvin. That is a question. The next line of action is to collect data. This is where a good number of students fail. I keep telling my students that physics is calculated. Calculations in physics are done using the 5 C's: correct equation, correct substitution, correct evaluation, correct answer with SI unit, if any. So right now we are going to collect our data to solve question BII. From what I have here with me, we collect the data as follows. So 1 point power is equal to what? 1.2 kilowatts. 1.2 kilowatts. What's given by 1.2 kilowatt? Kilo means 1,000. So this is the same thing as what? 1.2 exponential 3 watts. That is the value of that. The next thing is the mass of water. So the mass of water, let's say MW is equal to 800 watts, 800 grams. So we convert it to kilogram by divided by 1,000. So 800 grams divided by 1,000. This go, this go, this go, this will have 8 all over 100. And this will give you 0.8 kilogram. Let me confirm. 8 over 10 will give you, yeah, I was correct. And that is that. And then we have the initial temperature of water, θ1, let's say θ1 is equals to 20 degrees Celsius. And then we have the boiling point of water, which is θ2 in this case, as 101 degrees Celsius. The specific heat capacity of water, C subscript W, is equal to 4,200 joule per kilogram per Kelvin. So we are done with our data collection. So if your data collection is correct, you are going to substitute also correctly. So the next thing is the equation. So we recall that H is equal to MC change in theta. Call this equation 1. Also that H is equal to IVT. Call this equation 2. So we equate equation 1 with equation 2. So we have MC, we have IVT is equal to MC change in theta. And you know that power P is equal to IV. So this implies that PT is equal to MC change in theta. So we are going to say that T, which is a parameter that was needed in this equation, T was not given. T was not given in the equation. So we have to calculate for T. So our T right now is equal to MC change in theta all over what? P. So we are going to substitute correctly now. Our mass is what? The mass of the water is 0.8. Specific heat capacity is 4,200 times change in temperature. So you have 101 minus 20 degrees Celsius. So divided by power. Your power is what? 1.2 exponential 3 watts. So if you do that, we're going to have 0.8 times 4,200 times 101 minus 20. What do you have? You have times 81 divided by 1.2 exponential 3. 1,200, you have 1,200. So this figure divided by this, what you have? 0.8 times 4,200 times 81. We give you a figure like 272,160 divided by 1,200. So that figure divided by 1,200 will give you what? Let's do it again. 272,160 divided by 1,200. So therefore, our time T is given as 226.8 seconds. 0.8 seconds. That is our time. I would love you to go through these calculations. If there are any mistakes, you can comment on this video so that I can effect the correction. But I believe there are no mistakes here. To this, we have come to the end of this experiment. Thank you for your time, and I would love you to appreciate the effort put into this video by sharing this video to secondary school students who are finding it difficult to understand physics experiments. Thank you, and God bless you. Up next, I will upload a video on mechanics. Thank you and stay safe.